Okay, so now we're moving on to chapter 3, and the first section is talking about exponential functions and their graphs. So chapter 3 is going to deal with exponential and logarithmic functions, which turn out to be very common, especially the exponential function in calculus and in science. So you'll definitely see these again if you take calculus. So if we look at the right-hand screen, we see an exponential function f of x, which has a base a, and it's denoted by the function a, which is the base raised to some power x. So in this case, the variable is the exponent in the exponent. For polynomials, x was the base, you could call it, sort of, and then the exponent was a fixed value. Now a has to be greater than 0 and not equal to 1, because if so what does that mean? Well, if you have a negative number, then raising a negative number to an even power gives you a positive number, and raising a negative number to a negative or to an odd power gives you a negative number. And what does it mean when it's something in between? And if you let a equal 1, 1 raised to any power is just 1, so it's really not a function. Okay. So here's our first example here, just a simple case. So if we have this function where you have 2 raised to the x power, so x is the independent variable, which is plotted along the x-axis or measured along the x-axis, and the value of the function y is 2 raised to that power. So in this case, the base would be designated as 2. So let's just plot a few points, just evaluate the function and see how this graph represents this function. So what we can do is we just set up a table where we have x, and then we have 2 to the x, which is f of x. So if let's start with 0. So that's 2 to the 0 power. Any number raised to the 0 power is 1. And you can see 0, x, y, 1 is a point on that curve. If you have x equal to 1, the value of the function is 2 to the first power, which is 2. So if you go here, 1, 2, that's the next one. 2 to the second power is 4. That's 2 times 2. So 2, 4. And you can also have negative numbers as x. So then you'd have 2 to the negative 1 power, which is 1 over 2 to the first power, which is 1/2. So that's this point right there. And that's one thing to consider, if in terms of exponential functions, we kind of understand things like, let's say y equals 2 to the, where x is an integer, a positive integer. So let's just look at the case where x is a positive integer. So let's just look at a couple of different cases here. So what does this mean? The exponent means how many times you multiply the number by itself. So here we just have 2 without multiplied against anything. So any exponential function raised to the first power is just the value, the base. Here the exponent is 2, so that means we take 2 times 2. So we have 2 multiplied by itself. So that's 4. 2 cubed, that means you take 2 times 2 times 2, which is 8. And if you add 2 to the 4th power, it's equal to 2 times 2 times 2 times 2, which is 16. So those integer ones make sense. positive integers. From a negative integer standpoint, you'd have 2 to the minus 1 power, which is 1 over 2 to the first power. If you had 2 to, pardon me, to the negative 1 power, 2 to the negative 2 power, it's the same as 1 over 2 to the second power. So here we just have 1 over 2, which is a half. Here we have 1 over 2 times 2, which is 1 over 4. If we had 2 to the minus 3 power, that's 1 over 2 cubed. And 2 cubed is 2 times 2 times 2. So when you have a negative exponent, you rewrite it as a fraction where the negative exponent becomes a positive exponent, and then you just use the normal definition. Now, what happens if you have y equals 2 to the 2.4 power? Well, how do you multiply 2 by some fraction like that? So I'm just going to give you a little kind of an introduction here to think about. So one of the properties, we'll see one of the properties of exponents is that if you have 2 raised to some power, you can break this up into, say, 2 to the second power times 2 to the 0.4 power. So when you have the same base, you add the exponents together. So this part we know how to do. That's just going to be 2 times 2. So we have this 2 to the 0.4 power. What the heck does that mean? Well, another thing about there's this relationship between fractional exponents and roots. So if I said what's 2 to the 1/2 power, that's the same as the square root of 2. If you have 2 to the 1/3 power, that's equal to the cube root of 2. And 2 to the 1/4 power is the 4th root of 2. So what does this mean? What does the square root of 2 mean? It says, you know, what number multiplied by itself gives you 2. So you'd say x times x equals 2. And so the square root of 2, square root of 2 is x. Okay, so if x times x is 2, then x is going to be equal to the square root of 2. So the number, when multiplied together, gives you 2. So we know that x is, we can put it in our calculator and we get 1.414. And if you take, and that's, I've only rounded it off to 4 decimal points, 3 decimal points. If I multiply these two numbers together, I'll get approximately 0.00. So the square root of 2 is this. And the same thing with the cube root of 2 is what number multiplied by itself 3 times gives you 2. So if you take x times x times x is 2, then x is equal to the cube root of 2, which I don't know what the cube root of 2 is. So going back to this question, you can rewrite 2 to the 0.4 power as 2 to the 4/10 power. And so this is a fractional exponent. So another way to think about this is it's going to be 2 to the 4th power, take the 10th root of 2 to the 4th power. And 2 to the 4th power would be 2 times 2 times 2 times 2, which is 16. So it's the 10th root of 16. Anyway, let's think about that one for a minute. Okay, so this is kind of our simplest exponential function with the base 2. Now all exponential functions have similar shapes, just like back in chapter 1 we had quadratic functions, cubic functions, square root functions. So they all have this general shape when the base, well, when yeah, when you go from negative x, it approaches 0 at negative x. As you get closer, further, larger and larger negative x, and as you get larger and larger positive x, it increases very quickly, exponentially. Okay, so this is this explanation of what that means. So I was trying to make a joke here. You can't just have 0.4 of 2. And so this is what I was alluding to earlier. The 4/10, 2 to the 4/10 is the 10th root of 2 to the 4th. Okay, so here's parent function for the exponential function 2 to the x. We already plotted that. So there are certain important things that we know about functions. Is we know the domain, and as you can see, all the possible x values, you go from negative infinity. So 2 to the negative infinity power approaches 0. And if you put, you can do 2 to the infinite power, and that goes to infinity. So the domain is the possible x values, which goes from negative infinity to positive infinity. The range, you can see that e to the x is always a positive, not e to the x, but a to the x, or 2 to the x in this case, is always a positive quantity. So it goes from 0 and never equals 0. So y is greater than 0 and always less than infinity. So it's kind of like the quadratic function. It's always a positive value. The x-intercept, or the y-intercept, is always 1. Is 1 for 2 to the x. Turns out the y-intercept for 3 to the x is 1, and 4 to the x is 1. So they always have the same y-intercept. And that's because any number raised to the 0 power is 1. And it has no x-intercepts because the range, it doesn't cover all real numbers. And the horizontal asymptote depends which way you're going. If you go to negative infinity, it has a horizontal asymptote at x equals 0. But as far as the x greater than 0, the horizontal asymptote does not exist. And it is continuous, which means that there are no breaks in the function. Something like, step function is not continuous. So that is the general shape. And we've already talked about this. When x is negative, you change the negative exponent to a positive exponent. And this is kind of just stretching out the domain less than 0. So -1, -2, -3, -4, -5, -6. And again, this approaches 0 pretty quickly. Just like on the other side, when x is greater than 0, it increases rapidly also. Now, again, looking at this parent function, 2 to the x, how does the negative sign affect it? Well, it depends upon whether, well, you can't really have the -2 inside here, because then it would be a base that's something other than a positive number. So this is the negative of 2 to the x. So you can kind of think of it as negative, put a parenthesis here, 2 to the x. So you evaluate 2 to the x, and then you take the negative sign. So just like other functions, when you put a negative sign out in front of the base function, you reflect it across the x-axis. So remember, if you have y equals x squared, it looks like this. If you do y equals negative, and again, I'm going to put a parenthesis there to emphasize the negative is outside the parenthesis. So it's equal to negative x squared. What that does is it reflects it around the x-axis like that. And again, there's not an equivalent. You can't put the negative sign in the middle inside there. Now what happens is if you put the negative with the argument, so instead of moving the negative sign in here, which we would normally do for other kinds of functions, we actually put the negative with x. So it's kind of like, the equivalent here would be y to the negative x. And what we found out there was earlier that reflected across the y-axis, and the same thing happens here. If we look at the function y equals 2 to the positive x, it looks something like that. So when you put the negative here, it reflects across the y-axis. So the kinds of transformations that you can see, first you've got your parent function, and the parent function shape is not just one shape, it's dependent upon what the base is. So if you had 3 to the x, it would be different than 2 to the x. The vertical shift is exactly what we've seen before. If you add a constant outside of the parent function, all that does is shift it up or down. So if you add something, add a number, shifts it up. If you subtract a number, it shifts it down. Now, to have a horizontal shift, the constant is added or subtracted in the exponent. So what you would have here is, if you have, for example, a to the x minus 2 is x minus h, kind of like the way we did it in chapter 1, h would be 2 because you're x minus h. So x minus 2 would shift this parent function to the right. If it was x plus 2, it would be x minus a negative 2. So let me just show that. So if we had a to the x plus 2, that's the same as a to the negative. Actually, we don't put the negative out front there. We have x to the minus negative 2. So that would be 2 to the left. To reflect it across the x-axis, the negative sign is out in front of the whole exponential function. And as I pointed out, we never put the negative sign inside there. And to reflect it across the y-axis, the a to the x becomes a to the minus x. And then you've got stretching. So vertically stretching it, you multiply by a constant, which is between 1 and infinity to stretch it, and between 0 and 1 to shrink it. If it's equal to 1, it doesn't change at all. So if you had e to the, 3 times 2 to the x, that would be stretched. If you had 1/3 times 2 to the x, that would be shrunk. And then horizontally, the multiplying term is inside the exponent, inside the exponent. For stretching it horizontally, which is the same as shrinking it vertically, b in the exponent term would be between 0 and 1, and to shrink it, b is greater than 1 and less than infinity. And those are kind of qualitative things. If you'd have to plot the function to know exactly how much it changed. So here's an example. So the blue curve is the parent curve, which is 2 to the x. If you multiply the exponent by 2, this goes with this red curve. And because 2 is between, this b here is between 1 and infinity, it shrinks it in the horizontal direction. So it pushes it this way. If this was equal to 1/2, which would put you up here, it stretches it in the horizontal direction. It just makes it, if you think about it, this exponent gets bigger faster, so it tends to grow more quickly when this is greater than 1. where this is a half, the exponent doesn't grow as quickly, so it tends to hang around a little bit longer. And then there is a special base besides 2 or 3. It has a value of 2.718281828. And to demonstrate what this number represents is if you take 1 plus some decimal equivalent of the fraction associated with the exponent. So what does that mean? It means 0.1 is equal to 1/10. So because the exponent is 10, we add 1/10. And so what that is 1.1 raised to the 10th power, you get 2.5937. If you do it for 100, so we take 1 plus 100 to the 100th power, so that's 1.01 to the 100th power, gives you 2.7048. If you do that for 10,000, so if you do that for 10,000, 1 plus 0.0001 raised to the 10,000th power, and you could do it for 1,000,000. And at some point you can say, well, what's the value if b goes to infinity, which is this? So 1 over infinity, 1 plus 1 over infinity, the infinite power. And so it doesn't go to infinity, it goes to a finite value, which is this value for e. And that has lots of significance for calculus and stuff like that. So that's a special case of an exponential function, where the base is not an integer and it's this specific irrational number. So this is an irrational number, meaning that it goes on forever. And it looks like it repeats, but I think it doesn't. At some point it doesn't. Okay. What am I trying to say about this curve? Yeah, I think what I was trying to demonstrate here was if you have a circle and you draw a line that touches the circle at one point only, we call that a tangent line. So you should remember that from geometry. So any line that's touching the surface of the circle we call a tangent line. And you can do the same thing for exponential functions. You can see I've got this red curve and then this red straight line, and the red straight line has a slope at this point such that it only touches the red curve, and that's what's called the slope of the curve at that point. So for something that's linear, the slope is constant, but for a curve that's a curve, not a straight line, the slope of what we would call the tangent line varies. And it turns out that for the exponential function e to the x, that the slope of the tangent line is has some special characteristics, which again you'll learn about in calculus. Okay, so that's it. Let me delete that. So this is 6th edition homework for this section. So basically what we've talked about is that you have the exponential function. There is a parent function with for each base, and then there are transformations just like we had for parent functions in chapter 1, the same kinds of transformations that you make. You can do the same thing with exponential functions.